For almost a century, we've been told the quantum world is just fundamentally weird, blurry, random. But what if that's not the whole story? What if there's a hidden reality underneath it all, one where everything is perfectly clear, predictable, and makes a certain kind of sense? Today, we're going to dive into Bohmian Mechanics, a totally fascinating and, yeah, pretty controversial alternative to the quantum theory we all learned in school. It all comes down to this one deceptively simple question. Think about it. When an electron zips from point A to point B, does it actually follow a specific path to get there, even if nobody's watching? How you answer that, believe it or not, puts you on one side of a massive divide in the world of physics. Now, the standard answer, the one in most textbooks, is a hard no. It says that before you look, there isn't even really a particle in a specific place. There's just this cloud of possibilities. The whole idea of a path is literally meaningless. But the Bohmian answer? It's a radical, defiant yes. The path is absolutely real, it's definite, and it's being guided by something else, a hidden wave. Right, so this standard view is called the Copenhagen interpretation, and for the better part of 100 years, it's been the consensus. It basically says that the job of physics isn't to describe what reality is, but just to predict what our lab equipment is going to say. It's like a form of laboratory bookkeeping. And as for what happens when we're not looking, the official answer was, don't ask. Seriously. But not everyone was willing to just give up on reality that easily. And that brings us to the story of this rebel theory, an idea that was defeated, buried, and yet somehow just refused to stay dead. This rebellion was all about what philosophers call the realist impulse. It's this deep gut feeling, held by giants like Albert Einstein, that the whole point of physics has to be describing what's actually out there, what exists independent of us. A theory, they argued, should give us a clear picture of the universe, not just a bunch of equations to predict lab results. Man, the history of this idea is a real roller coaster. It kicks off in 1927. Louis de Broglie proposes his pilot wave theory. But at the legendary Solvay conference, the heavyweights of quantum mechanics just tear it apart. So much so that he actually abandons his own idea. So the theory just lies dormant, dead in the water for 25 years, until a brilliant physicist, David Bohm, who was super unhappy with the standard view, rediscovers it all on his own and perfects it. And then, much later in the 90s, it gets another polish into the sleek, modern version we have today. But let me tell you, Bohm's revival was not met with a standing ovation. The resistance was intense. This quote from Robert Oppenheimer, yeah, that Oppenheimer, just says it all. If we cannot disprove Bohm, we must agree to ignore him. I mean, wow, they couldn't find a flaw in the math, so they basically decided to just pretend it didn't exist. So how does this rebel theory actually work under the hood? Well, the central idea is incredibly intuitive. The best way to think about it is like a surfer on the ocean. Okay, first, a key term, primitive ontology. It sounds super complicated, but all it really means is, what's the list of stuff a theory says is fundamentally real? For Bohmian mechanics, this list is beautifully simple. The only thing that's fundamentally real, particles, in space. That's it. That's the whole list. Now, both theories use this mathematical thing called the wave function. In the standard view, this is just an abstract tool. It's a recipe for calculating probabilities, the odds of finding a particle over here versus over there if you decide to look. But this is where Bohm's genius really shines. He said, wait a minute, the particle is real and the wave function is also part of the story. It acts as a pilot wave that guides the particle along. So the particle is our surfer and the wave function is the wave. The shape of that wave tells the surfer exactly where to go. The surfer always has a real position, but its path is totally determined by the wave it's riding. And this isn't just some loosey-goosey analogy. It's described by a very precise mathematical law called the guidance equation. Now, you don't need to know the math here, but just looking at it shows the core idea. There's a simple, deterministic rule that takes the shape of the wave and spits out the exact velocity for the particle. No randomness, no probabilities, just pure, clean guidance. The modern view makes this picture even cleaner. Instead of thinking of a physical wave pushing the particle around, we now think of the wave function more like a law of nature itself. It's not a physical thing, but it's the instruction manual for the particle. Kind of like how the law of gravity dictates how planets move without physically pushing them, the wave function is the law that dictates how particles move. Okay, so Bohm's theory gives us this awesome world of real particles following real paths. No more weirdness, right? Problem solved. Well, not exactly. this beautiful certainty comes at a price, and it's a very, very strange one.
To get this crystal clear picture of reality, the theory absolutely requires something called non-locality. And if that rings a bell, it's because this is the very same concept that drove Einstein crazy. He famously called it spooky action at a distance. What it means is that particles can be connected, influencing each other instantly, no matter how far apart they are. It's a fact that really messes with our everyday ideas about space and time.
So what does this actually mean? It means the velocity of an electron right here could, in principle, depend on the exact position of an electron in the Andromeda galaxy right now, instantly. The entire universe is interconnected in this deep, immediate way. But here's the absolute kicker. This isn't some weird flaw in Bohm's theory. The physicist John Bell proved mathematically that any theory that has a real, definite world and matches the predictions of quantum mechanics has to be non-local. It's an unavoidable feature of reality. There's no escaping it.
So this leaves us with a kind of cosmic menu of choices. As you can see, there's no free lunch in quantum physics. Every interpretation has a pretty hefty price tag. You can stick with the standard Copenhagen view, but you have to give up on a deep reality. You can choose the many worlds interpretation, but then you have to believe in an infinite number of parallel universes. Or you can choose Bohmian Mechanics. You get one real, deterministic universe, but you have to accept this spooky, instantaneous connection between everything.
Now, you might be thinking this is all just fascinating philosophy, but the battle for reality is heating up like never before. This century-old debate has officially moved out of the armchair and into the laboratory, and it is more relevant right now in 2026 than ever before.
For decades, these kinds of questions were just brushed aside as metaphysics, untestable, and therefore not real science. But that has completely changed. Thanks to some absolutely incredible technology, physicists are now designing experiments that can actually start to probe these foundational questions and maybe even distinguish between these different pictures of reality.
And the frontier is just buzzing with activity. Just last year, a super controversial experiment by Shar Glazova and her team claimed they'd measure particle speeds that contradicted Bohmian predictions, and it kicked off a firestorm of debate. At the exact same time, other researchers are using these revolutionary weak measurement techniques, letting them gently peek at a particle's path without totally disturbing it. And what they're finding is astonishing. Trajectories that look remarkably like the hidden paths Bohm's theory predicted all along. So this leaves us with a profound choice about the very nature of our universe. Which one would you rather live in? A reality built on the random roll of the dice, where things only become real when we look? Or a perfectly predictable clockwork universe, held together by a mysterious, invisible web of connection? For the first time in a century, we actually have the tools to maybe, just maybe, find out. The battle for reality has officially begun.